Now, if we look at our track circuit diagram, this should give us some relevant information about where our track circuit is. In this example here, track circuit A, our yellow track, goes all the way from one side of the level crossing to the other side of the level crossing. It does go through a set of points up to a limit of shunt. Now, for those in the know, you will notice they are coloured, the track circuits. On the up, sky colours, yellow and blue. Blue for the sky, yellow for the sun. On the down, green and brown. Green for plant life, brown for earth. So the way to remember it is on the up, yellow and blue, on the down, green and brown. Sky colours for the up, ground colours for the down. Now, you will get combinations where you'll end up with, say, track circuits, two up lines, where the two track circuits may go through a set of points, and you'll have a colour there that will match. So to differentiate them, one of them will be purple. You will also see on this diagram here, we have black. Now on the Midland region, black means not under our control or not track circuited. So this is not track circuited. This here is under Darley-Dale's control. So that track circuits there that are shown in black, they are nothing to do with us, they're to do with Darley-Dale. We just have a repeat indication from them as well. On the Western region, it's entirely different. You can have blues, browns and blacks, and they entirely mean different things than they do on a different region. Every region has its own standards. Here we have a slightly more complex track bonding diagram. This is Great Rock signal box on the Midland region, and here we have quite a few track circuits outside the signal box. This site copy diagram here has positioned the signal box so you can identify where you are, and as you can see here, jumpers are clearly marked that take the voltage and flood it round to the other rails. So if we were to have a look at this simple track circuit here, this is a set of points through 32s. Here we have TB, track feed positive leg, the track feed negative leg, and they both flood down straight through the track to the relay. This is the relay negative, obviously, feed negative, relay negative, feed positive, relay positive. As you can see through the point work itself, we have the insulations at the end of the track circuits there to break that up, and this becomes another track circuit up here. If we follow up through these track points here, we will notice that we have an insulated interrupter on that track circuit, and I'll show you what that does in a minute. Basically, if the train goes beyond the limits of the track circuit, it will shear off this insulated track circuit interrupter and occupy the track circuit permanently. One other thing to notice on the bonding diagrams, the positives and negatives are defined differently. So for instance, the positive leg is defined as the thick black line, the negative return as the thin black line, and you can clearly see this here on these two track circuits. And this is quite handy if you're following around the track circuit diagram. Another thing to notice, in this diagram in particular, it shows you the insulations on the points, generalised. So for instance, on these set of points here, 32 alphas, that half semicircle there defines the insulations within the points themselves. It should be taken as obvious that there's insulations on the points. However, they're included on the track circuit diagram for faulting purposes. Here we are at Consall signal box on the Turnip Valley Railway. I'm just going to take a brief look at the actual main parts of the track circuit as such. So you can appreciate our relay cupboard with our interlocking is over there, and that takes our indications back to the interlocking and to the signal box for controlling the signals. So what we have here is we have our relay end terminations just there, which go off into the cupboard, and this will be one of our rails. So here we have our positive rail, and here we have our negative rail. Every section of track, these are all 30 foot, I think 30 or 45 foot, is bonded up with the bonding wires just mentioned. And as you can see, we have our voltage upon our track circuit, 1.37 volts, carried all the way through. So the positives carried all the way through from the feed, and the negatives carried all the way through from the feed, all the way down there. And in there is a power supply which feeds into our track circuit. That carries it down. So as you can appreciate, the setup of the ballast conditions is quite important. So this is good ballast here, but what you don't want is saturated ballast with a ton of muck in it and chemicals such as factories, because that will alter your ballast resistance and alter your voltages that you energise and de-energise the tracks at. Also, you want good drainage. So here we're on a steep banking, which is quite good. And the sleeper condition as well. These are concrete sleepers. We have some wooden ones down there through the points. And as you can appreciate, under every sleeper, we've still got the original rubber pads. So it will go over time, and that causes you some problems. And also there's reinforcements through the sleepers. You don't want them bridging out through these. On modern bits of track, what you tend to have is the pandrol system, where the pandrols hold the rails together, and they have a small insulated coloured plastic, we call them chairs and settees, which sit under that and isolate them down from the sleeper to the rail itself. So should anything going short in the sleeper, it doesn't go through to the rail. Standard 867 feed set, and these come either for mounting on a flat shelf, that's some of the standoff feet which are under here, as you can appreciate, or for rack mounting via the mounting holes onto a unistrut type shelf. 2 transformers inside, setting resistors, which are these, and they come with power input, which is on the back. So we have our 110 input, we have our positive and negative output to our track. What we also have, as you can see, we can set it for 9 or 20 ohm resistance, and also long and short tracks. They kick out around about 67 volts, so they're quite high power. AC immune, so if you're going to use this, you need to match it with the correct relay. It has been known for these to be run with shelf type track relays before, but with extra resistances in. It depends on what your Heritage Railway has available and what you're using. No standby batteries attached into this. You can't do that. It will absolutely cane the battery. So that's the 867 feed set with no standby battery attachment, and it does have a little circuit diagram, which is handy. So if you're going to set these up on the track, on a long track, you'd set it to the long setting. It's quite a short track, you set it to the short setting. And obviously match your relays for 9 and 20 ohm resistances on your relays, which you should be able to find out quite easily if you look at your relay coil. It should be stamped there as an R number. This is a slightly older but slightly different track feed set. Here you have your 110 input again, with your balancing settings on your primary side, so you can up or lower the voltage to match. And on your output side again, your track positive and track negative outputs. Just a smaller unit. This one doesn't have a long or short setting. It's not AC immune, as you can see from the label here. And kicks out about 2 volts, 1 amp. Now this will work quite happily with standard shelf type track relays. It's about the track circuit. It is the limiting or balance resistor. It serves a couple of purposes. The first is the most obvious one. If you consider this is our test setup, it's not powered up at the moment, but we have our feed supply. Now our positive feed supply, in this case here, goes down to our track, round to our relay, returns down the other rail, and would go back to our power supply. If we were to put a train on here, this would act as a short circuit, and yes, it would stop the current coming from the supply from reaching the relay. That current would then be shunted back round to the power supply. However, it being a short circuit, it would likely damage the power supply, or at the very least blow the internal fuses, the inline fuses. So we need to prevent that short circuit. So to do that, we need to add a balancing resistor in there. And that resistor is in series with either the positive or the negative leg. And what tends to happen there, once you get a short on the track circuit, then the resistor takes the load, so it will not blow the power supply. Drain clears the track circuit. Again, the power is free to flow all the way to the relay and energise the relay. Also, the resistor is used for setting up the shunt values, because as you can appreciate, the differences in resistance between the rails depends on the sleepers, the condition of the ballast, how impregnated the ballast is with things like mud, ash. A lot of locomotive ash can cause a lot of problems in track circuits. You can short it out because it is an acidic means. You can also have, as one of your tests on track circuits, is to remove the supply by pulling the fuses, and then with a meter on the track, see how long after 2 minutes that the voltage drops down slowly, because the ballast will have what's known as a battery effect, depending on what chemicals are in that ballast, the makeup of the ballast, where it is, local conditions. There are so many things. Some track circuits near factories, some track circuits that are heavily inundated with mud, they will maintain a voltage there, and that voltage could potentially hold the track relay up. So there is a formula for that. Over the 2 minutes you watch the voltage, see what it drops to, and within certain criteria whether the track passes or not. And this is just our demonstration little test set here. So you can appreciate that. And that's what the balancing resistor allows you to do, to set up your shunting values, but also to protect against a short circuit when every train comes on the track circuit. And of course we have bonding wires. Now, as you can appreciate, the section of rail here is only held together to the section of rail here through fish plate joints, which every summer the PUA come, take apart, oil up the backs off and put back together again. So if you relied entirely upon just the bolts and the fish plates taking the current through for your track circuit, it wouldn't be great, and the PUA wouldn't be able to do anything maintenance wise, because they'd be constantly breaking the circuits down. So as S&T, what we do, we have our bonding wires which go through. These are doubled up. Some railways just single bond them, some railways double bond them, some railways triple bond them. Depends on your maintenance regime, and they're simply held in at the back by some tapered pins, and they hammer in quite easy and just hold the circuit as one. What you tend to do with your wires is you tend to have this nice bend back on, because obviously, as you can appreciate, rails expand. PUA want to come down, move things out the way, put spanners on, etc, etc. So you want that little bit of movement in it. So we put that kind of expansion in there just for the sake of it. Insulated block joints come in many different types. This is a 4-hole. You can have a 6-hole pre-made one. This is a 4-hole Benkler. Benklers allow you to be able to take the block joint apart. They come as 2 side plates, one on this side, one on the far side, and then you have a set of insulations that go just inside on the plates as well, and bolts that then fit through. When this has been put together, you want to make sure that the bolts aren't smashed through with the hammer, otherwise they will damage the insulations on the inside. Also, if you just drill the rails, you want to make sure you get rid of all the swarf out of it with the magnet, otherwise that will slowly eat its way into the nylon plates. And also in the middle, you'll notice this is a T-piece. Now, depending on the quality of your track, this can get knocked to heck, and the top of the T-piece starts to burr over. You can get burring faults, small bits of swarf carried across by the rails, the train wearing the rails down, that eventually shorts it out, especially on sharp curves where it will actually carry the swarf along. Now, one of the important things to talk about with track circuits is track circuit stagger. So for instance, if this was the positive leg, that was the negative leg, we would design our next adjacent track circuit to have opposite polarities. So the positive would go to a negative, negative would go to a positive. Thereby, if there was a fault or a failure of the insulated block joint, it would drop the tracks, and we'd be able to know there's a problem then. So I can just simply show you this by putting the meter across. As you can see, nothing there at the moment. Put it across and register a voltage. If I push hard, I can actually get 0.6 of a volt on there. So that's showing you that the rails are staggered, and we can test this. We'll put our meter on there, and put our meter on this side, and there should be opposite polarities. Obviously, with block joints, the rail insulation piece in the middle there, called the T-piece, these do suffer with wear and tear on the locomotives and wagons and carriages over the years, and they do wear out. And also you can get movements on the side plates as well. As you can see on here, we have our main insulation and we have our backing insulations. The main plates themselves are on both sides, the insulated plates, they have a ferrule through. So when the PUA comes to knock the bolts in, they should be extremely careful not to just hammer them in. If the rails are slightly wide, it's not a great idea, because you'll just strip the insulation off and drop the track circuit. Likewise, if you're cutting rails, you ought to make sure that all the swarf is gone before you put the plates on. Nowadays they have a magnet to drain all the swarf off before they put the side plates on, and you want to make sure that plates don't drift too far and end up catching on the chairs themselves, because that can also cause problems as well. Another thing you can talk about on track circuits is quite important. Obviously 2020, not many trains are run on heritage railways, so you have a lot of the rusty railhead conditions. You can see here where the actual wheel of the train has been clearing the railhead, and the rest of it is still entirely rusty. and you can end up with a lot of rust contamination. Now in sidings that can be got round with a two-tetic strip, which is a welded stainless steel strip on it, but you don't want to put that on the running lines, because on the running lines that will cause a lot of ride problems. Also wear and tear to the wheels. So there are various ways around that. Sidings, depression bars to prove the train's there, or a lack of train. Two-tetic strips, welded two-tetic strips as I previously mentioned. And also moving off to a different subject would be AC track circuits. AC has a tendency to go a lot further than a DC track circuit, and also tends to blast through the railhead contamination quite a lot. We don't suffer much with the leaf fall problem that a lot of railways suffer, because obviously we run heritage trains which are heavier. The locomotives are heavier, the carriages and wagons are heavier than the modern sprinter units and the DMUs. And also we've had a tree management programme for the last few years to keep our trees managed. So as you can notice, even though there's leaves on the ground, still haven't rotted in January, there's none squashed onto the railhead. And I haven't seen a single one squashed onto the railhead since I've been here actually, which is good, because it means they've all got blown away. These are our track feed leads and our track relay leads. So at either end you will have these, and what they simply are is the incoming track cable terminated onto a crimp which goes here. There are two galvanised pins which go through the rail. They're hammered into place. Some back nuts which go on, non-locking back nuts. Tighten them up, and then you put your L bracket on, as we call it, the L plate, which goes on to the rail. And your crimp goes round, and then your locking nuts. Also what you can have is a metal clip that clips to hold this onto the rail. This is bullhead track and we don't have any clips unfortunately, so we'll just keep as that, not in the way of the train. You can also do this single pin, that's another way of doing it. And another way, which we used to do, we used to just drill the holes through the rail, put a piece of bond wire through, two bond pins on the opposite side, and we used to just solder this on. We used to call that goal posting, because it looks like a goal post. That's an older way of doing it. But there are various different ways of doing it. Some railways do it with just the single pin, so the wire will just go straight into the track and it'll just be a bond pin on the back. That's another way of doing it. It depends on which way your heritage railways set out. These tend to be the modern standard now, using the L brackets. Additional DC track relay consists of, in the older form, a case, contacts in, two coils on top, a coupling bar through the centre, and you'll notice each coil is connected both on its input side to a central stud terminal, then to the other coil, and then back out. And it was known in the past, if one of these coils went down and had an open circuit within it, you were able to take that coil out and bypass it by taking the strap and putting it onto this, which meant only one coil would be in use. That was an emergency get out in the past. It's not something you would do nowadays. You would change the relay. Again, standoff feet underneath to keep it off the surface. You don't want things freezing down. And the contact arrangement depends on the relay at hand. You can either have two front arm and back, or you can have four front arm and back. It just depends on the type of relay. They tend to come, as I was taught, you can see this on here, they usually have a little label just here. Now this older one actually has a label on it. It's quite heavily worn, so you can't really make it out. D3s and D6 types. So the way I remember this is a D3 has a pick of roughly 0.3 of a volt, and a D6 has a pick of roughly 0.66 of a volt. So you can kind of work them together. D3, 0.3, D6, 0.66. And one of the unwritten rules of thumb is you never put the track voltage over 1.5 times the pickup voltage, otherwise you will saturate these coils and magnetise them up permanently. And then what will happen is, as you try and take the voltage off the relay with the train, it takes its time to drop, and you don't want that. You want a clean, quick drop. So you can appreciate, coils R1 and R2, centre stud terminal, so comes in, goes through the coil to the centre stud, goes to the other coil, back out, and off you go. So your posi and neggy to your track relays, to your track links, and also a central coupling bar through to hold the magnetism through, which is what this top affair is for. You see it on this one. So there's your central coupling bar. The wire wound coil, some of them you will actually see it still has the details imprinted on the back of them. I'll give you the details. Some of them have this all metal printed tag label on them. More modern ones tend to have the label on the side here. Not always there. Problem with labels, they fall off. Unlike good old plate, which just goes up and you can't see it. And you can appreciate the contact arrangement inside. So here we have our front contact when the track is clear, our back contact when the track is occupied, our armature, and also we have this thin braided copper band which carries a current through because obviously the armature is moving, picking and dropping, picking and dropping. So if we look at the insulations in a set of points, here we have our first stretcher insulation. We also have our sole plate insulation, and our stretcher insulations you notice are on the same side all the way down. Traditionally the drive rod isn't brought in on the same side as the stretcher insulation, it's brought in on the far side. You'll notice this has got a special bent rod for it. Here we have our insulated interrupter, as we call it. One leg comes in onto the rail, which is insulated, and then we have the knockoff piece on the other side, with the other leg going back out. As you can appreciate, if a train runs through the points, the flange of the wheel will shear this off here, knocking it off. This is a track circuit interrupter in its various pieces. So you have this screwing bolt onto the rear of the rail. You have the insulated ferrules to take you through the rails, as you can appreciate. You also have the insulated plate to go up against the rail itself. Then you have the actual cast part of the mechanism, and you can see where the shear off point is for the flange to come through and snap this off. There are older versions of these which don't actually have plate insulation as well. Those tend to be through the rail, direct and out. Not the greatest idea, because what you want is when this shears off, you don't want this to accidentally fall back onto the web of the rail and still keep the circuit up. You want it to shear off and break the circuit, hence the insulation here. Here we have a mid-rodding insulation. Traditionally you get one of these on the facing point lock. As mentioned before, tie bars are the P-way used to bring the gauge in. This is a tie bar, has a clamp on one end, you put under the rail, clamp on the other end, you put under the rail. Should be insulated as well if they're on a track circuit, otherwise you will run the risk of putting a short on. The last thing to mention is the testing setup procedure for track circuits. Now, as anyone who's used one of these before would know, this is called a track circuit shunt box, and what we do is we use this for periodic tests and for setting up the track circuit. We're aiming for a resistance value of around 1 ohms, so that's, if I were to set this there, 1, and that side to 0, so that's 1 ohms. That's a nominal shunt value. We aim for around that. Obviously, the higher the voltage on the feed of the track, the lower the shunt, and vice versa. So it's a good 2-hand rule that. If you take one down, if the voltage goes down, the shunt goes up. If the voltage goes up, the shunt goes down. We don't want the shunt too high or too low. We're aiming for that perfect 1 ohm. And we also have a minimum setting. We also call that 0.5 ohms. We don't want to go below that. And when we're shunting, we attach these leads to the rails at the relay end, and we observe the relay slowly start to drop. So if we were to start at, let's say, 2 ohms, so that's 2 and 0.0, we would take the tenths down all the way from here. So actually that is now 3, so we'll go down to 1. Plus 1 is 2, and we'll start slowly decreasing it. 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 0.0. Once we reach here, we don't want to go through this. If we go through that, we'll allow the relay to repick. So we'll take this all the way back up and drop that one down. So now that is 1 ohm. And we start again. 0.9, 0.8 and 0.7. There are differences between AC tracks and DC tracks. As I mentioned, we don't want our shunt to go below 0.5, and we're aiming for a good pick of 1 ohm.
another little key thing to remember is we also want a pickup value, and the pickup value is nominally double the drop value. So if the drop that de-energizes a track is say 1 ohm, the pick will be around about 2 ohms. The only difference you will ever see is on, say, an AC track circuit, where they can be very close together, so you could have a drop of say 0.7 and a pick of 0.9. But these things are in your standards for your own railway. But that's the standard DC shunt box. There are different versions of this, and that's what we use to set it up, put on at the relay end on the track leads.